Well, welcome. In this video lecture, we are looking at the book Think Python, How to Think Like a Computer Scientist. We're looking at the second edition. The authors are Alan, Jeffrey, and Chris. I'm going to be doing video lectures. My name is Arthur Solomon. I'm going to be working with you throughout these videos. Thank you. Welcome, Chapter 6, Fruitful Functions. So in this chapter, we're looking at the ability to do return values in a function. We're going to be exploring our Boolean functions more, and we're going to look at the flow of execution of a program. So first of all, a return value. Essentially, when we call a function, we should have the ability to return a value, or at least that is the ability. When we're talking a fruitful function, they can also return an expression. However, we also have these things called void functions, and they will return no value. So it really just depends on the type of function that we are actually going to be working with, because that determines the type of return that we're going to be looking with. Here we have an example of our default. We have a function for area. We're feeding in a variable radius, and we are returning an appropriate response. We're returning math times pi, math pi times radius squared. Again, the double stars, we know that as an exponent. So this is pi radius squared. And then the return value would be the radius. So in that example, that would be a no value, because it's not actually returning the radius, it's just returning the outputs. So we have what's called our fruitful function, and that is, it for whatever reason keeps removing my tabs in PowerPoint, but it would take our function radius, and we are actually piping it to a variable, and we're returning that variable. So this is actually going to be our fruitful function, because it could be returning a value. Here it returns the expression, not specifically a value. So code that appears after a return statement or any other place that will follow the execution can never actually be reached. This is called dead code. Return basically should be able to return a value. You'll notice we have a function where we are comparing a value of x. If it is less than 0, we're returning a negative number. If it is greater than 0, we're returning a positive number. You can tell negative x, that will be positive x. Well, if x is less than 0, it has to be a negative number. So in a fruitful function, it's a good idea to ensure that every possible path through the program actually has some form of return statement. That way, we can ensure no dead code. This function is incorrect because x happens to be 0, so neither condition could be true. So that's why it's always a good idea, again, to verify, to test, to troubleshoot, to ensure all paths for a program can actually truly be allocated, or could actually be ran. If, for example, x is set to 0, well, x is not going to be less than 0 or greater than 0. X would be equal to. So we can actually modify this to be less than or equal to, or we can add in a third if statement. If x equals 0, then return something else. So as an exercise, we can compare functions and look at two different values. So here we have two values, x and y, and we can also do a return. So if 1 is greater than x, return 1. 0 if x is equal to y, and negative 1 if x is less than y. We can actually write that if we want to verify. So at the end of 6.1, it asks the question. It wants as an exercise to write and compare a function that takes two values, x and y, and do these computations. So let's see if we can do that. I went ahead, I already wrote out the code. I'm asking for a number for x. I'm capturing it as an integer. I'm asking for a number for y. I'm saving it as an integer. I have my function call. And I'm comparing value x and value y. So why value x and value y? When I call the function, I have the original variables x and y, and I just want to keep those values separate. What I'm going to do is I'm going to compare if y is larger than x, if y is equal to x, or if y is less than x. If x is smaller, return negative x. If they're equal, return just the normal value of x. If x is greater, return a positive x. And I'm also doing a line at the bottom so that I can keep my numbers separated. And so down here in the bottom is going to be my actual output. So I'm going to go ahead and run my code. So please enter a number for x. I'm going to enter 1. Please enter a number for y. I'm going to hit 0. And so it captures my 1 and it captures my 0, and then it leaves the function and it prints my returning value of x, which happens to be 1. So why did it not do the print options? Earlier when we talked about dead code, this is dead code. The order matters. So I rewrote this in a different module where it's going to actually do the print function first and then return the code. Everything else is identical. So play it again. 1 and 0. And you'll notice it prints our dotted line, so we can keep those variables separate. I like this because it allows me to show my work more incrementally. And again, this was just one of the exercises at the end of 6.1. So moving on, we have 6.2. And this is about incremental development. So to deal with increasingly complex programs, we want to be able to do a process where we can do our steps, where we can make sure one part's functioning, and then we go to the next part, then the next part, and we step them through. We don't have to worry about doing all of it at once. So there are normally 3 key aspects to this process. Start with a working program and make small changes. At any point, if there's an error, we should have an idea of where the error is because we're making only small changes and we're testing along the way. Use variables to hold intermediate values so you can display them and check them. You'll see in some of my previous videos, as I'm creating variables, I may print the variable in the functions so I can see what those variables are. Third, once the program is working, you may want to remove some of the scaffolding or consolidate multiple statements, compound the expressions. Basically, you clean it up so that you know what's going to be there. However, you also want to document the program, and you may want to make a copy of the program with all of the additional help functions that you've included. That way, if there is an issue, you can return back to that. As an exercise, let's use incremental development to write a function called hypotenuse that will return the length of a hypotenuse of a right triangle given the lengths of the other 2 legs as an argument. Record each stage of the development as we go. Alright, so according to our text, we are looking for the distance, which is equal to x2 minus x1 squared plus y2 minus y1 squared, and we're looking for that square root. So we have the distance between these variables. So the first section they say is go ahead and give us this function right here. We know that this clearly is not going to be true because the return of 0 is not appropriate. It won't compute the distance. It will always return 0. So we need to go ahead and take this and work this and develop it. So it later goes on and has us modify this. So let's go ahead and let's try to compute the distance between x2 and x1. So you'll note that it's already having our variables x1, y1, x2, and y2. So it actually wants us to create a new variable, dx, and we want to take x2 and have x1 subtracted from it. To do the same thing for y, so dy equals y2 minus y1. And to make sure this is working, we actually want it to print some examples. So we will do dx is, I will do a comma, and I'll have it print the variable dx. I'm going to do the same thing with dy. Yes, it's still going to return our zeros. However, at this point, that is okay. So for our testing purposes, x1, x2, y1, y2, we're going to go ahead and hard code these numbers for our testing. It wants us to use some variables. Let's go ahead and use 1. Alright, don't like that. Okay, there it goes. So for x1, it wants us to use 1. For y1, it wants us to use 2. For x2, it wants us to use 4. And for y2, it wants us to use 6. So we have our variables, we have our function. Next thing, we actually have to have some type of call to call our function. All right, so for what I'm going to be doing right now is I'm going to go ahead and comment out the variables. I'm just going to print it as a call function. So distance, x1, y1, x2, y2. I'm going to go ahead and run it. So I'm getting dx is 3 and dy is 4. And that's appropriate. I'm going to go ahead and clear my screen. So now that we know it's returning the appropriate calls, now that we know that it's actually doing what it's supposed to be doing, we can work on the next part, the next step. That's what I mean by incremental. We do it step by step. So pretty much I'm just going along with the book's example. So part of this function before the return, I'm going to go ahead and I'm going to create a d squared. So ds q. And I'm going to go ahead and set that equal to dx star star 2. That's going to say take dx, square it, and we're going to add dy. Double star is again the exponent. So we're squaring these. And I'm going to go ahead, I'm going to print out I'm going to go ahead and do dsq is, and I'm going to print out dsq. Run the function again. So dx is 3, dy is 4, 3 squared plus 4 squared, 9 plus 16 is 25. So we know that is the appropriate number. If we're not sure on the math, we can easily do two more print statements, and that would be dx power 2, and we do the same thing, dy power 2, and what we'd end up doing is and make sure the tabbing is correct. I'm going to go ahead and clear this, run it again. That way I can see dx squared is 9, y squared is 16, and that way we can see to make sure the math is correct. That way, again, incremental steps that we can do to verify the functionality. Again, we have a running program, and at this stage we can start checking the output, which should be 25, and that is what we're getting. So we have a few different things that we could be doing. Instead of doing it this way, I'm going to go ahead and make a new module. Copy this to the new module. I can go ahead and I can get rid of my print statements. I know that this is functioning correctly. Well, that return statement is a little weird. So what I can do is I can now use some of the math functions that are built in. So now that we know what these numbers are, I need to go ahead and I'm going to have a new variable, result, and I'm going to go ahead and set result, and that will be equal to math.sqrt square root, and I'm going to set that to my DSQ number. And I want to make sure that this is printing out the correct number. So I will go ahead and print the SQR is, and go ahead and print results. Again, I'm still returning 0, so that's fine for now. See, it does not like that part at all. The issue is math.square root is a proper function, but sometimes Python likes to be a little bit moody, so we need to go ahead and do import math. That will let us use the math functions. Go ahead and hit the run option, and you'll now see the square root is 5. So that is the appropriate response. So we're almost done. We're going to go ahead and we're going to remove this print. And we no longer want to return zeros. We want to return our results. That means we actually want to print our results. So I'm going to have print the return of that function. And there it is. If we want to change these numbers, just like we did in 6.1, we could do a capture request for the coordinates, and that way we can save the different coordinates. That way we wouldn't have to hard code it. But the exercise didn't quite go that far. So this would actually be our incremented developed code. You'll notice that our original had lots of print statements as we stepped through it. Our end result did not have a single print function in our function. The print was actually part of the function call. So moving on, we have our 6.3, our composition. Remember that the functions can also be nested. We can also do loops. Our loops can be nested, and we can do a combination of nested and loops in any form. Remember, these are the building blocks of how we can do certain functions. I'm not going to do the composition example in the text because pretty much we've just did that in 6.2. So moving on, we have our 6.4, and that will be our Boolean function. Again, these functions can return a Boolean value, and it's often very convenient for hiding more complicated tests inside the functions. Essentially, we're looking for if a number is divisible, we're looking yes or no. That's all we want. Boolean is yes, no, or true and false. So here we have a definition. We have a function of our number is divisible function. Essentially what we're doing, we're comparing two numbers. And if the x modulus y, if it's set to 0, then we know it's divisible. Else we're going to have it flagged as negative. It does not want to go to the next screen. There it goes. So as an exercise, write a function that is between three variables that returns true if x is less than or equal to y and false otherwise. So we're looking for x is less than or equal to y, which is also less than or equal to z. All right, so I'm going to start a new program. All right, so the function is divisible, and we have three variables, x, y, and z. I'm going to fix that spacing. And so we already know the goal is we want if x is less than or equal to y and also less than or equal to z. If that is the case, we want it to return a true statement. Else, return false. So what we're going to have to do is divisible. Let's go ahead and let's do 1, 2, 3. So this should yield a true result. First of all, when trying to run it, first we end up with an error statement. Again, we're looking for unexpected indentation. Why is that? That is because we did an if statement and we didn't end it with a colon. When we went to name our function, I forgot diff, but we also needed the colon. Run it again. All right, so I cleaned it up. I did forget a colon up there. So I created my appropriate function, labeled it, colon at the end, run it. I'm going to get a message that's saying true is not defined. So I'm going to go ahead and get rid of true, capital T, and you're going to see what variables I can actually return with. True is actually a Boolean value, so I'm going to go ahead and fix those. So now colorization is correct. I'm going to go ahead and run it again. So it didn't give me any new errors, so I'm going to clear the screen, Run it again. So why is it not giving me a value? Well, first of all, I actually didn't say print anything, so print so I'm going to go ahead and try that again. So I got a true statement. So again, trying to combine what we've been discussing in previous chapters as we work through it, incremental, looking at the errors as we go through to ensure we understand the error output, and being able to combine those to complete the exercises. So we've completed the exercise, writing a function, is between, and then we use that to verify. A common mistake is capital Z, or one of these capital, when the variables were clearly all lowercase. Remember that Python is case sensitive in this regard. So yeah, these should all be lowercase. And we have to make sure our colons are also there. So let's jump back. So we've done our 6.4 Boolean functions. So with 6.5, we have about more additional recursions. So we've only covered a very small subset of Python. It's very interesting to know that the subset is a complete programming language, which means this is one of the languages that can pretty much do anything that we can do as written language, we can express in Python. One interesting thing to note is that it also being complete is it's a complete programming language, which means that anything that we've computed so far can also be expressed in this language. Any program that could be written could be rewritten only using the language features that we've learned so far. It may be more difficult. We've not learned all of the functions or all of the looping abilities, but we definitely could do everything with what we've learned so far. So to prove that claim, it's not transversal, non-trivial, let's go ahead and complete an additional exercise. So let's go ahead and accomplish by our exercise in the reading. It's going to have us do a factorial function, which I'm not going to write those out. That's going to make this video a lot longer than I wanted to. But essentially, the goal with this is understanding that with our recursive functions, we can accomplish almost anything that we need to with the functions that we know so far. It's just letting us know that we know a ton. It's just a matter of putting the pieces together so we can expand on that knowledge. So here's an example. So making a recursive call to find the factorial of n minus 1, and then we can multiply it by n. So we can do a function, n is set to 1, or sorry, n is equal to 0. If it is, return 1. Else we can do this process of recursive. We can set our factorials to do the appropriate math function. Again, way outside of what I want to do for this video, but we can do recursive algorithms to find more complex math programs, or to do more complex math computations. We can write the programs knowing what we know. So 6.6 is about a leap of faith, and that is looking at and understanding the flow of execution and the way to read a program. It can be way overwhelming. An alternate way is called the leap of faith. When you come to a function call, instead of following the flow of execution, we can assume the function works correctly and returns the right value. We can have faith that the function is written correctly. We've already basically been practicing this leap of faith when you've used built-in functions. We use the math square root function. We could have done the computation values to verify, or we could just assume that it works and trust it and move forward. So the same is true of recursive programs. So when you get to the recursive calls, instead of following the flow of the execution, we should assume that the recursive calls work and that the return calls should be correct. So we have one more example. Mathematical function is I can't pronounce that, so I'm not going to try. And what we can do is we can write this as a function. So after factorials, the most common example of recursively defined mathematical functions is this example. If you try to follow the flow of execution here, even for a very small value of n, it's going to get really in-depth really quick. So we can assume that the two recursive calls will work correctly and that it's going to do it correct. That's it. We can move forward. So with 6.8, it's about checking our types. One of the problems is, as we're doing this, we have to understand the arguments, the call functions, things like that. So here, if we have a factorial of 1.5, we may get a runtime error saying maximum recursive depth. What does that mean? So basically, it may look like an infinite recursion. So how can that be? Because the function has a base case where n is set to 0. The problem is, if n is not an integer, it can miss the base case and thus do the recursive forever. The goal is to have an argument that will eventually be able to reach its base case so that the loop can end. So in the first recursive call, the value of n is 0.5. In the next one, it is negative 0.5. From there, it gets smaller and smaller, or more negative, so it will never actually become 0. Thus, it will run forever. So we have two choices. We can try to generalize the factorial function, or we can make a factorial check and the type of its argument. So the first option is called the gamma function, and way outside the scope of this course. So we're going to focus on the second option. And essentially, it's going to act as a guardian. So for the example, we can do a function called our integral factorial. Alright, sorry about that. I fixed it. Sometimes the PowerPoint likes to mess up the spacing. So here we have a nested set of ifs and else-if statements. We can use the built-in function instance to verify the types of arguments. While we're at it, we can also make sure the arguments are positive. The first base case will handle non-integers. The second one will handle negative integers. If we get past both checks, we know that n is a positive number or is set to 0. We can also prove that the recursion will terminate. This program will demonstrate a pattern sometimes called a guardian. The first two conditions will act as the guardian protecting the code that follows from the value that might cause an error. The guardian will make it possible to prove the correctness of the code. Sometimes it's really good to build in test cases to make sure that we can test and verify without having to worry about going in and looping forever. We get to our debugging section, and again, we've already talked about a few different types of areas. One of the big ones might be breaking large programs into more smaller functions. That way we can have natural checking points for our debugging. So there's three main possibilities if a function is not working. First, the function may not be working if there's something wrong with the arguments the function is getting. There might be something wrong with the function if the post condition might be violated. Or there's something wrong with the return value or the way it's being used. So we can actually do our incremental development to get through all three of these and verify that our function calls are not an issue by doing our incremental development like we did in 6.1 and 6.2. So our glossary with things like temporary variables, dead code, incremental, scaffolding, guardians, and again, these are just some of them. They are not all of the key terms, these are just major ones. Lastly, there are 5 exercises in our end of chapter that you guys should be working through, 6.1 through 6.5. I'm going to do separate videos explaining the exercises. If you have any questions, definitely feel free to reach out. Thank you. That concludes this chapter. If you have any questions or concerns, please feel free to reach out and leave me a comment or a question. I'll try to get those answered as quickly as I can. Again, thank you, and I look forward to working with you in later modules.